Today's this one equation can describe a surprising range of phenomena.
Okay, hold on. Let's unpack that a bit. I am picturing the blueprints, but maybe with some flashing neon signs that says, flux and gradient. What are those exactly?
Alright, let's bring it down to earth. Think of a crowded street fair. Like flux is the flow of people, right? How many people are passing a certain point, every minute. So high flux means lot of foot traffic.
Got it. High flux. Lots of people bustling about. What about the gradient? Does that tells us where they all are headed?
Precisely. Imagine one stall is giving away like free samples. Suddenly you have a high concentration of people there, right?
Okay.
That difference in people density between the free samples and other areas, that's the gradient. It's what drives the flow like from the less crowded spots toward the free stuff.
So the steeper the gradient, the bigger the difference in the people's density. The stronger the pull towards the free behavior.
Exactly. And the transport property in this scenario would be like how easily people can navigate the crowd. Think wide walkways versus narrow congested ones. That determines how quickly people can respond to that driving force of the free samples, even if the desire is strong.
Okay, I am starting to see the analogy here.
Yeah.
How do we go from crowded street fairs to the actual molecules and energy?
The beauty is the principle remains the same, whether it's molecules diffusing, heat spreading, or momentum transferring in a fluid. We can use this framework to describe how it happens.
So that this stuff being transported, whether it's molecules or heat, momentum, that's like our crowd, right?
Yeah.
And the concentration, temperature, and the velocity difference, those are like the allure of those free samples, creating the gradient that drives the flow.
You got it. And just like the ease of moving through a crowd, each stuff has its own property that dictates how easily it flows.
Okay, this framework is starting to feel pretty powerful. But is it just a general idea, or there are actual laws that use it?
That's where the classic transport laws come in. Fick's law of diffusion,
Yeah.
Fourier's law of heat conduction, and Newton's law of viscosity.
Yes.
We have discussed this in earlier podcasts, correct? These are the like specific blueprints for how different stuffs move, all built on that same framework.
Oh, okay. Now things are getting interesting. Let's take closer look at these laws. Starting with the Fick's law, what it deal with diffusion?
Well, think about how a drop of dye spreads in water. That's diffusion in action. Fick's law tells us about the rate of spreading depends on two things. How steep the concentration difference is, so how much dye versus water, and how easily those dye molecules can move through the water.
So if I use the really high concentrated dye, it will spread faster because the gradient steeper, right? And
Yeah.
the dye that's more water friendly will also spread quicker.
Exactly. And that water friendliness, that's what we call the mass diffusivity. It's the transport property in this case.
Okay, so that's mass moving around. What about energy? Is that where the Fourier's law comes in?
You bet. Imagine you're holding a metal rod and one end is heated. Like we have taken an example of coffee in the earlier one. Fourier's law says that heat will flow from the hot end to the colder end, just like our crowd moving toward the free samples.
I am starting to see the pattern here. So the steeper the temperature difference, the faster the heat flows, right? And I guess different materials would conduct the heat different rates, like
Yeah,
different
it,
rates.
it would conduct heats at different rates too, right? And that's where thermal conductivity comes. It's the transport property of for heat flow. Think about how a metal pan heats up so much faster than the ceramic one.
Got it. So the mass has its diffusivity and heat has its conductivity. What all is left? We have got the momentum, right?
Precisely, and that's where Newton's law of viscosity enters the picture. Momentum. So we are here we are talking about physical objects moving from one place to another, not anymore. Think of it more like the transfer of motion within a fluid. Imagine stirring honey. It's way harder to stir than water.
Right. Oh yeah, definitely. Honey is thick and resists the movement.
Exactly, and that resistance is due to its viscosity, which is transport property in Newton's law. The higher viscosity, the more difficult it will be to get the fluid moving, and the slower momentum is transferred within the fluid.
So the viscosity is kind of the stickiness of a fluid. It determines how easily the motion of the liquid flows through it.
Yeah, that's good way to think about it. The velocity gradient, like how much the fluid speed changes across its layers. That's the driving force here. Thicker fluids, they resist that change more, leading to slower momentum transfer.
I think I am getting the hang of this now. We have got the Fick's law for mass diffusion, Fourier's law of heat conduction, and Newton's law for momentum transfer in fluids, all based on the same align equation. But earlier you mentioned something called molecular flux. How does it fit in all of these equations?
Excellent question. We have looked at these specific laws, but let's zoom out again to that big picture. Molecular fluxes is a way to quantify the rate of transfer for any property, not just mass, energy or momentum.
So it's like the universal language for describing like how much something is moving through a certain area over the time.
Exactly, and the equation still holds. That way I have told you earlier, molecular flux equals gradient of driving force times the transport property. It's just that the unit of flux will depend on what's being transported.
So if we are talking about the mass flux, we might use like moles per second, but if heat flux, we would use the joules per second. Yeah, something like that.
That's the idea. And it's all about keeping track of what's moving and how we measure it.
This is the pretty mind-blowing thing.
Yeah.
It's like we have this master key that can unlock the secrets of how anything moves from tiniest molecule to the large scale systems. But hold on, how do we actually measure these fluxes? It's all seem very theoretical so far.
Yeah, that's where things get really interesting. We have experimental techniques for measuring each type of flux. For example, we can measure the concentration of a substance at different points in time to determine the molar flux or the temperature difference across a material to figure out the heat flux.
So it's not just an equation on chalkboard. We can actually quantify these things in the real world.
Yeah.
That's make some powerful thing, right?
Yeah.
We can take these principles and apply them in all the problems to solve them.
Absolutely, and that's the where diffusivity has come in.
Diffusivity. Okay, I am intrigued. What are those things that relate all of this?
Remember how we have talked about how friendly a dye molecule is. That's essentially its mass diffusivity. Similarly, thermal diffusivity tells us how easily heat can travel through a material, and momentum diffusivity, often related to kinematic viscosity, that describes how momentum spreads within a fluid.
So diffusivity are like the speed limits for how fast different things can move through a different materials.
Yeah, that's a great way to think about it. There are those crucial transport properties that we plug into our flux equation.
This is getting really exciting. So if we know the diffusivity,
Yeah.
a particular substance we can predict, like how quickly it will spread, how fast it will flow through, how easily it will transfer the momentum.
You got it. And that's why diffusivities are so important for understanding and predicting transport phenomena, in a whole range of applications.
This has been incredible journey already. We have gone from a big picture of transport phenomena to the specific different fluxes.
Yeah.
And how we are seeing the diffusivity play a crucial role in determining how fast things move.
Now, here we have changed our method a little bit so that you can grasp the concepts through visual representation and formulas more easily. Now, we have discussed our three laws, which are, you tell me, Kaushik, which are the three laws we have
obviously.
discussed?
First is Newton's law of viscosity,
Which is tau ix is equal to minus mu dvx by dy. And what was the similarity that we have discussed earlier is like momentum flux will be equal to transport property into velocity gradient. Now the next law, which is
Fourier's law of heat conduction, which is Qyx is equals to minus k times dt by dy, which is equals to energy flux into transport property into temperature gradient.
yeah, and similarly for fixed law of diffusion we have jy star is equal to minus dab dca by dy, which is now we can associate with molar flux is equal to transport property into concentration gradient.
Right, now we will find the similarities between these three laws, which can be molecular flux is equals to transport property into gradient of some driving force. Right.
Now we can observe the similarity here. Molecular flux is equal to transport property. In the Newton's law of viscosity it is mu. In the Fourier's law of heat conduction it is minus k, and in
Fixed law
of
of
diffusion
it is dab.
yeah. So now we'll try to make it more similar,
Yeah, while making some changes in their gradient in driving force, we will make some changes so that we can make it more similar with each other. We
Okay.
will find the comparison between each other.
Yeah, now let's dive into that. Now we will have our molar flux will be equal to mole per unit volume, as we can observe here, which is unit wise,
Yeah,
correct?
dCA by dy, which is equals to mole per unit volume. Now we will change this other two laws according to this formula.
Yeah, so that we can make it more similar, correct? Yeah, so we can do the same for energy flux, which will be energy per unit volume. Now, how will we make dt by dy minus k dt by dy into energy per unit volume? So, what we can do is
by multiplying and divide it by rho Cp actually.
Rho Cp. So when we will divide and multiply by rho Cp, the term in the differential term will be energy per unit volume. Now, hence we have make two laws more similar to each other as compared to earlier.
Now it's time for Newton's law of viscosity to be changed with momentum per unit volume. So we will multiply divide it by rho Vx.
Actually, Vx is already there, so we just have to multiply it and divide it by rho.
Right.
Now we can observe that we have made these laws more similar as compared to earlier by just changing their units. Now we have make all the three laws more similar by
Now we already know what is DAB. DAB is the mass diffusivity, right? Now other constant we will change into the diffusivity term, like K by rho Cp, which can be considered as thermal diffusivity, represented by alpha, and mu by rho is called as momentum diffusivity, which is denoted by nu.
Now what we have earlier what's transport property into gradient of driving force. Now to make it more similar, we have like unit wise we have made it more similar, and we have now our special terms, which is mu by rho momentum diffusivity, k by rho cp thermal diffusivity, and dab mass diffusivity. So here we can see a pattern of diffusivity into momentum per unit volume,
which can be called as molecular flux. So overall, we can conclude the similarities between the three laws by molecular flux is equals to diffusivity times gradient of quantity per unit volume.
Now we'll move on to the next portion of which is comparing their terms, all the terms and all the properties. First one which we have come with is our molecular flux. Then we will discuss about their transport property in each cases like momentum, energy and mole for each one of each. Now
Overall, we are going to summarize in the tabular form the each terms. First is molecular flux, which is for momentum transfer tau ix, energy qy, and for molar, that is jay. And the transport property for each terms are mu, k, and dab.
as we have seen earlier.
Yeah. And similarly for gradient of driving force accordingly, which is dvx by dy, dt by dy, and dca by dy.
So now these three terms we have discussed already.
Yes.
Molecular flux, transport property into gradient of driving force.
These are the basic formulas for the three laws.
Now for making it more similar, we have used some new terms which we have now derived. In the previous case we got diffusivity, quantity per unit volume, and gradient of quantity per unit volume. So now we got diffusivity for momentum, which is mu. And we got diffusivity for energy, which is alpha, and we got diffusivity for mole, which was same as the earlier case, which is dab. Now we got we like converted into quantity per unit volume for all the quantity for all the three laws, which we got for quantity per unit in momentum case. What we got, rho into vx, we multiplied and divided by rho, so we got rho vx. Then for the in the energy case, energy flux case, we multiplied and divided by rho into cp. Then in the mole case, it was same as the earlier ca. For making it the gradient, we know we have to like gradient means, as we have discussed and related to the physical and real life examples, gradient is the change at a particular point. So for the particular point we will denote it by d by dy here. Now here d by dy of quantity per unit volume, d by dy of quantity per unit volume, d by dy of quantity per unit volume.
Now these terms are even similar with the dimensions. Like the diffusivity part has the same dimension, which is meter square per second.
Yeah, for all the like fluxes, momentum, whether it be momentum, energy and mole, the unit of diffusivity will be meter square per second for what we have derived. Now let's talk about, let's like just for instance just take this diffusivity in a particular section. Now we will try to associate and relate each of these diffusivities with each other. How we can relate all of this diffusivity with each other?
With the help of dimensionless number, we will get the relation between the diffusivities with each other. The first dimensional number is
mu by alpha. What we did here is we took momentum diffusivity and we took energy diffusivity. Now we took the ratio of them, momentum to energy diffusivity, and we got our first dimensionless number, which is Prandtl number. Here Prandtl number is PR, which is denoted by PR, and which will be equal to momentum diffusivity by energy. We just have substituted the formulas for mu and alpha, which we have our earlier slides. Mu is mu by rho and alpha is k by rho cp, and when we'll substitute these formulas we will get our cp mu by k. Now next move on to the next diffusivity. What do you think of which diffusivities we can take ratio? So we will take ratio of momentum to molar diffusivity.
Right, now it's time for momentum diffusivity to the molar diffusivity, which we called as a Schmidt number. Schmidt number, when we elaborate the nu and dab, we will get the we will get the formula as mu by rho dAB, which is a Schmidt number. This says the dominance of molar diffusivity to the momentum diffusivity.
Yeah, that's a good point that you mentioned. Like, what will we get from dimensionless numbers?
Right.
These are telling us about the ratios. So while designing purpose, while anything which includes some momentum flux, which includes some energy flux, then we can compare. We can see which will be dominating in each cases through our Prandtl number, Schmidt number, and the one which will be discussing later. So let's discuss that one first. Then we will tell this significance of these dimensionless numbers. So last one is our Lewis number, which is alpha by DAB. Here, alpha is energy diffusivity, DAB is molar diffusivity. So what we are doing here is we are just taking the ratios of diffusivity from each of the terms, and we are getting a dimensionless number which have a greater significance. Now, let's talk about the significance. So, in Prandtl number, we have taken momentum diffusivity to energy diffusivity. Now, if Prandtl number is greater than 1, then we will have more momentum diffusivity and less energy diffusivity, which is denoting, which is showing that the momentum flux is more dominating there as compared to energy flux, and we can design and adjust the parameters according to that. So that's where dimensionless number come to our help.
Similarly, for Schmidt number and a Lewis number, if this three-dimensionless number is greater than 1, then the numerator term is more dominating, and if it is less than 1 or it is in fractions, then the denominator term is more dominating, which we can conclude in the designing purposes. Like if the momentum flux is more, we will design according to the formulas of the momentum flux. If energy flux is more dominating, we will use the energy formulas for designing the piping or some reactors and or any other things. So there is big significance of dimensionless number in the designing purpose.
Now let's see what I have shown, that order of magnitude. So do we know that order of magnitude of Cp, mu, K, rho, dAb? Now do you know what this terms mean? What is Cp, what is mu, what is K, what is rho, what is dAb? Obviously you know. So for gases and liquids, we'll first discuss order of magnitude for Cp, rho, K, K, rho and dAb. Then we'll discuss our Prandtl, Schmidt and Lewis number for gases and liquids. So firstly, let's discuss this one. So for Cp, we have 10 to the power 3, 10 to the power 3 order of magnitude. Now let's compare our Prandtl number, Schmidt number and Lewis number for gases and liquids.
Similarly, a Prandtl number for gases is 1 and for liquid is 10. Schmidt number for gases is
actually
1.
All the three dimensionless numbers for gases will be 1. When we will put the order of magnitude of each Cp, rho, mu, whatever the form will become in formulas, we will get our gases where magnitude will be 1, and for liquid we will get for Prandtl number we'll get
10 raised to power 3 for Schmidt number, and similarly 10 raised to power 2 for Lewis number.
This is a bit of you have to make ratta of it. Let's get back to our old way now. Ever get that feeling like you really want to understand something complex but without having to go back to school for it?
Right.
Like you just want that shortcut to the core of it.
Absolutely.
And that's kind of what we are going for here on the deep dive.
Yeah.
We are all about talking this kind of intricate topics and really breaking them down so you can walk away feeling like, okay, I got it now. I don't need to be an expert to at least grasp the basics. And today we are diving into something called convective and total flux. And especially in those situations where you have got multiple things mixed together, those multiple component systems.
Multi-component systems.
Yeah, so it might sound kind of technical.
Yeah, it does.
Right, like something you'd only encounter in lab or some highly specialized field, but the principles here, they're actually surprisingly relevant.
They are.
To all sorts of things happening around us, like think about a warm breeze carrying scent of flowers, or even just mixing paint colors to create a new shade. At their core, we are really talking about how things move and mix. And these concepts of convective and total flux, they are key to understanding that movement and that mixing.
Absolutely. And it's really important in a lot of applications too.
Yeah, definitely.
Like designing an efficient air conditioning system.
Okay.
Or understanding a new nutrient spread in plant.
Yeah.
Not at all very practical.
It has real world applications. Okay, so to guide us through this, we have got a couple of resources that what we are looking
Sounds good.
Okay, so what on the one side we will look at molecular flux, which will give us those fundamental concepts,
Right.
and there is one another which will display a detailed explanation of convective and total flux. So we have got the basics and a deep dive. Now our mission today, if you want to call it that,
I'm in the game.
is it really to get a grasp on what these fluxes actually are?
Okay.
What are their components and how they all relate to each other?
It's like there's plan.
Obviously there's a plan, and we really want to make this clear and engaging.
Yeah.
So you can understand the core ideas without getting lost in the equations.
Right, because those can get pretty hairy sometimes.
Yeah, for sure.
So where do we even start with this whole flux thing?
Yeah, it is a bit abstract when you first hear it.
It is.
So let's unpack that first.
Okay.
What we have gathered, the general idea of flux is all about the amount of something that passes through a specific area over a certain amount of time. So it could be stuff like molecules, it could be energy, it could be even something like momentum.
Okay, good, got it.
So imagine a doorway in a busy building, sorry, my bad. So imagine a doorway in a busy building. The flux of people would be like the number of people walking through that doorway every minute or every hour or whatever.
I see. So it's like a rate of movement.
Exactly. It's a rate of movement through a specific area.
Okay, that makes sense.
And in our case, instead of people, we are looking at this different properties moving through a defined space.
Right. Okay, so like heat moving through a wall or something like that?
Exactly. That give us this really handy way of thinking about it mathematically.
Okay, let's hear it.
It says flux is essentially a transport property multiplied by gradient of driving force, as we have seen earlier.
Yeah, right.
Transport
property and a gradient of a driving force.
Yeah.
So those are our two key players here.
Yeah, it seems like
All
it.
right.
Now this might sound a little formal, but it's really powerful way to understand why things move.
So, okay, now I am intrigued.
And how readily they do.
Interesting.
So let's break down those terms a bit.
Interesting.
So this transport property, it seems to be about how cooperative a material is in letting something move through it.
So like how easily something can flow through it.
Exactly. And it mentions examples like diffusivity, thermal conductivity, and viscosity.
Okay, so like how thick the fluid is.
Yeah, that's viscosity.
Okay.
And it feels like there are inherent qualities of material itself.
Right. So like a material's personality when it comes to transport.
Yeah, exactly. I like that. So, for example, if we are talking about heat moving through different materials, would the transport property be higher for something like metal compared to wood?
Yeah, you got it. That's the thermal conductivity. And the metals are much better than that of wood.
Which is why metal feels colder to the touch.
Yeah, even if they are at the same temperatures.
Right, because it's conducting that heat away from your hand more quickly.
Exactly, it's whisking that heat away.
That's thermal conductivity. And then there's diffusivity.
Right, which is all about mixing.
Yeah, and like how easily one substance mixes with another.
Like how quickly sugar dissolves in our coffee.
Okay, perfect example.
Yeah.
So that's diffusivity, and then viscosity we talked about.
Yeah, that's the fluid resistance of flow.
So like honey versus water.
Exactly.
Yeah, honey has high viscosity, water got slow viscosity. Okay, now that makes a lot more sense with those examples.
Good, I'm glad.
Now what about this gradient of a driving force?
Yeah, that still sound bit intimidating.
Yeah, like it's going to push me around or something.
Right, like some kind of a physical force.
But it's not really a physical force in traditional sense.
No, it's like what motivates the movement.
Okay.
It's the different types of some property.
Okay. So
Across a distance.
it's a difference in property.
Yeah, across the distance.
So it's like a slope.
Yeah, you can think of it that way.
Okay. Like a slide hill.
Yeah, hillside, exactly. So the temperature gradient, for instance,
Yeah.
That's the different temperature between 2 points.
Okay.
And the heat is always flow from the hotter to the colder side.
Right. It tries to even out like.
Yeah, exactly. So that the temperature difference, that's the driving force.
Okay, so
in the
it's
system.
like nature wants everything to be at the same temperature.
In a way, yeah, it's always trying to reach an equilibrium.
Okay.
And then you have the concentration gradients too.
Okay, so that's like when you put a drop of food coloring in water.
Exactly, it spreads out because of the concentration gradient.
Okay, so it's moving from high concentration to low concentration.
Exactly, it wants even distributed.
So this gradient of driving force, it's really about that difference.
Yeah, it's all about the difference.
Okay, and that special change that creates the push for things to move.
Exactly, and to kind of even things out.
Okay, so we have got the willingness of a material to let something move.
That's our transport property.
Right, and then we have got the reason for that movement in the first place.
The gradient of driving force.
Okay, so now let's dive into convective flux.
Alright, let's do it.
What's the main idea there?
Some convective flux at its core is about the transport that happens because of the entire fluid is moving.
Okay, so the fluid itself is in motion.
Yeah, it's like a river flowing.
Okay.
And it's carrying the stuff along with it.
So it's not just about molecules randomly bouncing around.
Right, that's the diffusion.
Okay.
This is about the bulk movement of the fluid carrying the things along.
Okay, so it's like being on a moving walkway at the airport.
Exactly.
Like bulk motion is convective. Bulk movement is convective.
Exactly. You are moving because of the walkways moving.
I get it.
Okay.
This use is great analogy of boiling water.
Yeah.
I saw that. So what
So
will we see?
so you see the hot water is rising from the bottom of the pot, right? And it rises. It's carrying the heat with it.
Okay.
Up to the top, exactly.
Okay, so that's convection in action.
Yeah, the bulk movement of the fluid transporting the heat.
So it's like the fluid is a little delivery truck for heat.
Yeah, I like that analogy.
Okay.
The fluids, the vehicle, and the heat heats the cargo.
So fluid is the vehicle and heat is the cargo.
Yeah, right.
Okay,
exactly.
cool.
And this is where the things is getting really interesting when we talk about the multi-component systems.
Okay, so that's where you have mixtures of different substances.
Exactly, like air, which is mostly nitrogen and oxygen,
Right.
or seawater, which has all sorts of salts dissolved in it.
Okay.
And our sources point out that in this multi-component system, each component can have its own convective flux.
So each thing in the mixture is being transported by the overall flow.
Yeah, but at its own rate depending on its concentration and stuff.
Okay, that makes sense.
Now let's go into the more details about the multi-component convective flux.
So if we had a mixture like air flowing through a ventilation system, the flow of air would carry the nitrogen along.
Exactly, giving it a convective flux.
And it would also carry the oxygen along.
Right, with its own separate convective flux.
Okay.
Because they are both being moved by the bulk flow of the air.
But they might have different concentrations and stuff.
Exactly, and that affects the individual fluxes.
Okay, so in these scenarios, the convective flux for a specific component, it often depends on a few things.
It does.
Like the density of the fluid mixture, the velocity of the flow, and how much of that component is actually present.
Exactly, it's like the different types of cargo on the same truck.
Okay, I like that.
The truck's speed affects all the cargos,
Right.
but the amount of each type of cargo is specific to that item.
Okay, that's a really good way to visualize it. Right, so it's clearly a really important concept. It's fundamental when dealing with mixtures, convective flux.
Yeah, right. Okay.
So we have got this transport happening because the whole fluid is moving. right? Carrying everything along with it. Okay, so what is total flux?
Total flux equals the convective flux plus the diffusive flux.
Okay, so it's those two things combined.
Yeah.
But it also mentions that there might be other type of fluxes.
Yeah, depending on the systems.
But it's not always just those two.
Right. There could be the other things contributing the total movement.
Okay, so it's like saying if you want to understand how a pollutant moves in a river, we need to consider how much is carried by the flow of the water itself.
Right. That's the convective part.
Right. And how much is spreading out on its own
from the high concentration to the low concentration, right?
Right. That's diffusive.
Exactly.
And if we add this together, we get the total movement of that pollutant.
You got it. That's the total flux.
Okay.
In any kind of system.
Whether it's a simple fluid or a complex mixture.
Exactly.
Just to summarize and make sure we are on the same page.
Sounds good.
A convective flux is all about the bulk movement of the fluid carrying its component properties from one place to another.
Exactly.
And total flux is the sum of that convective part plus any contributing fluxes like diffusion
and potentially others.
Right.
Depending on the system.
Okay. And often to really understand the total transport, we need to mathematically combine those individual pieces.
Exactly. You have got to put them all together.
Okay, cool. I think I'm starting to get a handle on this.
I think you are.
So we have taken a pretty deep dive into convective and total flux.
We have
explored how convective flux is driven by the fluid's motion, which is especially important in multi-component system
where each component is kind of doing its own thing.
Yeah, exactly.
Within the overall flow.
And we learn that the total flux is sum of all those individual flux mechanisms.
Right, so the big picture.
And that often involves combining those different components
to get the complete understanding.
Yeah. And even though the math can get pretty intense, can the fundamental concepts themselves are pretty intuitive?
Yeah, once you break them down like we did,
it's really about identifying all the other ways something can move
within a system.
And then adding up those individual contributions.
Yeah, to get the total flux.
Okay, so it's like a big accounting problem.
Kind of, yeah. You are keeping the track of all the different flows
and then summing them up.
Exactly.
Okay, that makes sense.
Good.
Now, thinking about how convective and diffusive flux is combined, it makes me wonder that about like what other kind of systems.
Yeah, exactly.
Like not physical fluids at all, but maybe something like information flow in a social network.
Interesting.
Or the spread of ideas in a community.
I like that.
What would be the equivalent of convective and diffusive in those scenarios?
That is really fascinating question.
Yeah, isn't it?
It is.
Okay. It's like taking these principles and applying them to a whole new realm, like social media, etc.
Exactly, broadening the scale.
Yeah. So in the context of information flow, maybe convective movement would be like sharing of news or announcements through established channels like news outlets or community leaders.
Yeah, like top to down approach.
Correct. Exactly. And then diffusive spread would be more like rumors or informal information, I think.
Right, spreading organically through a personal connection.
Yeah, and like word of mouth. And then driving forces in those systems, maybe it would be things like the importance of the information, the strength of social connections.
Like how connected the people are.
Yeah, and the transport property would be things like the willingness to share information or the density of network itself.
Yeah, like how many connections there are.
So it's like we are taking these concepts from physics
and applying them to the social dynamics.
Yeah, exactly. It's a new, whole new way of looking at things.
It is, and it might give us some really interesting insights.
It could definitely open up some new avenues of research.
For sure.
Well, that's bring us to the end of our deep dive today.
It really does.
So now, but I hope this has given everyone a much clear understanding.
I hope.
Of what convective and total fluxes are.
There are key concepts.
Yeah, obviously. And why they are so important in transport phenomena.
Absolutely. They underpin so much of what we see around us.
Yeah, thank you so much for joining us in this exploration.
It was my pleasure.
And we will next we will deep dive into our formulas thing, and we will show you how the formula works.